This is Calculus section 5.6 on numeric integration. This is going to be another way that we use to approximate the area under a curve, because sometimes even with all of our integral skills, we're not going to have the ability to find the area under the curve any other methods. So here's the first example we're going to look at, and that graph is drawn down here, and it says we want to find the area under the curve from x equals pi over 6 to x equals pi. So we're trying to find all that region. And it says we're going to do it by splitting it up into 5 trapezoids. So then if I just draw some more vertical lines in here, there's region 1, 2, 3, and that's making regions 4 and 5. So here is R1, R2, R3, R4, and R5. And to find the areas of these regions using trapezoids, then I need to draw in these segments that go from the initial value to the final value. And we have all of these trapezoids. And if you look at this, it looks like our approximation is going to be pretty good. It's not quite getting all of the region, but it's getting most of the region. And recall, to find the area of a trapezoid, you add the two base lengths together and divide by 2. In other words, the average of the bases divided by 2 times the height. So to find the area of this one, we're going to find what is f of pi over 3, what is f of pi over 6. So add those values together, add those y values together, divide by 2, and multiply by this, which is the height. Now this height is going to be consistent throughout all of them. We can call that delta x. Pi minus pi over 6 is 5 pi over 6. So this entire length right down here is 5 pi over 6. We're going to split it up evenly into these 5 different regions. So each one of these regions has a height of pi over 6. And I've done some of this work, and this is some of the things I've just talked about. So delta x is equal to pi over 6. And I plugged in each of these x values from below. I plugged into our function, which is sine of x plus 1. So I evaluated f of pi over 6 and got this value. There's pi over 3, pi over 2, and all those values. And some of them are nice numbers like 3/2 and 2 and 1. Others are kind of complicated looking radicals. What I did is I stored each one of them in the calculator as different variables. And I'd encourage you to do the same. Maybe pause the video right here and do all of this work, have them stored into your calculator, because we're going to use those to streamline the next step in the process. So going back to this, area of region 1 is going to be f of pi over 3 plus f of pi over 6 divided by 2 times that height of pi over 6. Well, I have that is A, that is B, C, D, E, and F stored on my calculator. I have all those values from the work I did before. So if I did A plus B divided by 2 times pi over 6, that's region 1. That's what I have right here. The next region is going to be B plus C divided by 2 times pi over 6. Then the next region, C plus D divided by 2 times pi over 6. So this is giving us the area of all those different regions. And I have all those written up here on this line. This represents our entire area. Now it gets to be a little bit repetitive as each one of these terms gets added together, has a pi over 6 in it. So I factored a pi over 6 out. The other thing is, because we were finding the area of a trapezoid, base plus base divided by 2, I can factor a 1/2 out of all these terms also, put that out front. And we're left with A plus B plus B plus C plus C plus D plus D plus E plus E plus F. And I copied all of those down right here. But just by factoring out the GCF, we get all of these terms. And as I look at all about combining all of those, there's 1A, 2 B's, 2 C's, 2 D's, 2 E's, and 1 F. We have all this. Then simplifying that on the outside, I can enter this into my calculator since I have all those values stored, and very quickly approximate the area under the curve using all those trapezoids. And it's about 4.441. To see how close I am to the actual answer on my graphing calculator, I can enter this in, do the definite integral, and then compare those answers and see that my approximation is pretty good. Look at the next page of notes. We have this trapezoid rule, and what it's saying is if we're going to use trapezoids to approximate the area under the curve, the integral, the area under the curve, is approximately the area of all those trapezoids. And this doesn't necessarily look like a trapezoid formula right here, But that's essentially what we did on the previous page with that problem. You only have the first f of x value once, the last f of x value once, but all the other ones on the inside are going to be used twice. And then outside, it's b minus a over 2n. B minus a over n is the delta x, that's the width of each one of those trapezoids, and it's over 2 because in the area of a trapezoid, we have 1/2 the average of the bases. If we flip back to what we did just a second ago, this line right here is basically that trapezoid rule. First f of x value once, the last f of x value once, all the other ones in there twice because we see how they all added up together. Pi over 6 was factored out, that was our delta x. 1/2 because that was coming from the trapezoid, so this is really b minus a divided by 2n, which would simplify down to this. So at this point, I'd recommend stopping your video and try to do this next example. I have my work all laid out right here. This time the f of x values came out nicer, so I didn't store them on the calculator with different letters, but I plugged all these different values into the function. How did I know which x values to choose? Well, since it started at pi over 6 and ended at 13 pi over 6, I did my delta x, 13 pi over 6 minus pi over 6, then divided that by 6 to find the width of each one. That's how I knew where these were going to end up. And then again, I just followed through the formula and I got 8 pi. So see if you can work through that one on your own. The next example is using a function f of x, which we don't know exactly what it is, finding the area under the curve as best we can, so we're approximating it, from an x value of 3 to an x value of 25, given these f of x values. And one thing I notice is that these x values aren't spaced out evenly, so I'm not going to use a trapezoidal rule this time. I'm just going to make a really rough sketch of all the values we have, all the x values, all the f of x values, find the area of each of those trapezoids individually, add them all up to get the final area. So you can see what my answer is. Go ahead and pause the video, work through that on your own, and see if you can come up with that same value. The last thing in these notes is an AP question. This is from 2011, and here is what the question is. You see the different parts of it. We have a table that's given to us, and I'd encourage you to pause the video again and see if you can work through these problems. And in just a moment, I will work through these solutions as well. For question A, it says to use the data in the table to approximate the rate at which the temperature of the tea is changing when t equals 3.5 and show the computations. So between 3.5, that's right between the time values of 2 and 5. So if I found the slope between these two values, that would be approximately our rate of change at 3.5. It's not exact, so that's why we're saying just an approximate rate. So h prime of t, or in other words, h prime of 3.5 would be h of 5 minus h of 2 divided by 5 minus 2, and that gives us about negative 8/3 degrees Celsius per minute. And in part B, the meaning of this integral, notice out front we have the 1/10 of the integral going from 0 to 10. That represents the average temperature in degrees Celsius for the time interval from 0 to 10 minutes. And again, because there is no actual function, we use the table to come up with the values, and we're using trapezoids, which is why I'm including this problem right now. So find the area of all those trapezoids, add them together, multiply by 1/10, and we get the average temperature is about 52.95 degrees Celsius. So letter C, explain the meaning of the integral from 0 to 10 of h prime of t dt using correct units in the meaning. So we don't want to just say it represents the area under the curve if we were to graph it. What we're going to say is that, well, evaluating the integral, take the h of 10 minus h of 0, and we get negative 23. In other words, the t drops in temperature by 23 degrees Celsius over the time from 0 to 10 minutes. In question D, there's a lot going on to the problem, and we're told a little bit of information about the biscuits. At time 0, the biscuits were 100 degrees, so that's an initial value. That would be like an area under a curve. That's the starting temperature, plus the accumulation of the rate of change, so the integral from 0 to 10 of b prime of t. So we're going to integrate that. It would definitely be a calculator problem. And so if we do the 100 plus that integral, we get a total of 34.183 degrees. And the question says, how much cooler are the biscuits than the tea? So at the end of this time, the biscuits are 34.183, and we had that the tea was 43 degrees at the end. So if we subtract them, we get that the T is 8.817 degrees cooler. The biscuits are 8.817 degrees cooler than what the T was. On the final page, you can see how the AP board would score your various problems. 9 points total, and you can see the different things they were looking for those.